Welcome students for Haloalkanes and Haloarenes part 3rd. In this video, we shall be studying about physical properties and chemical properties of haloalkanes and haloarenes. So let us continue. Let us continue first with physical properties. Alkyl halides are colorless compounds and have a pleasant smell. Second, lower member are gaseous at room temperature, whereas higher members are liquids and solids at room temperature. Third, haloalkanes are polar in nature, and the reason behind it is the difference in the electronegativity value between the carbon atom and the halogen. Halogens are more electronegative when compared to carbon atoms. Let us see the first physical property, that is melting and boiling point of compounds. Generally speaking, boiling and melting points of alkyl and aryl halides are higher than the corresponding parent hydrocarbons. And the reason, students, for this, greater polarity as well as higher molecular weight as compared to the parent hydrocarbon. And the second reason, due to intermolecular forces of attraction are stronger in the halogen derivatives when we compare with their parent hydrocarbons. Second, for the same alkyl group, the order of boiling point is alkyl iodide with a higher boiling point when compared to alkyl bromide, and alkyl bromide is relatively greater boiling point when compared to alkyl chloride, and again alkyl chloride with a higher boiling point compared to alkyl fluoride. So students, in this case, alkyl group containing the same number of the carbon atoms, but if we vary the halogens with alkyl iodide, the maximum boiling point and the least boiling point for alkyl fluoride. And the reason behind this is the van der Waals force of attraction, which increases with the increase of the molecular mass. So students, here we are discussing about the covalent molecule. As a result, the force of attraction between the participating atoms is van der Waals force of attraction. Alkyl iodide has got more molecular mass when you compare with alkyl fluoride. Thus, boiling point of alkyl iodide is the highest among all the halides. Moving to the next one, for the same halogen atom, the boiling point increases with increase in the size of the alkyl groups. In this case, students, halogen atom, it can be fluoro, chloro, bromo or iodo atoms. Only one halogen atom would be the same for all the alkyl halides, but we are varying the alkyl group. In one case, we can consider N equal to 1, which is having only one carbon atom, so it can be methyl alkyl group. In the second case, it can be ethyl alkyl group, and so on. Thus, as the size of the alkyl group increases with the same halogen, Then for the highest alkyl group with the halogen has the higher boiling point. If you compare between ethyl chloride and methyl chloride, so ethyl chloride has got higher boiling point due to larger alkyl group. Next students, the boiling point of isomeric haloalkanes decreases with increase in branching. Let us understand this along with an example. The molecule is 1-bromobutane with a boiling point of 375 Kelvin. So this is first isomer of bromobutane molecule. Let's consider second. In this case, bromine atom is attached to second carbon atom. So the molecule name is 2-bromobutane molecule. Boiling point is reduced to 364 Kelvin because of the branching of one of the methyl group. Next student, the third isomeric form. In this case, again the branching has increased. The name of the molecule is 2-bromo-2-methyl propane. With the increase in the branching, the boiling point has reduced to 346 Kelvin. So students, from this example, it is very clear that if isomeric structures of the haloalkanes is there, then with the increase of the branching, the boiling point gradually decreases. Let us now consider haloarenes, that is aromatic ring covalently bonded with a halogen. Example, chlorobenzene. The boiling points of haloarenes are nearly the same as those of haloalkanes, but with the same number of the carbon atoms. Next students, para-dihalobenzene has higher melting point as compared to ortho and the meta isomers because the para-dichlorobenzene is more symmetrical in structure and thus have more compact arrangement in the solid state. Whereas students, for ortho and meta isomers of dichlorobenzene, they are having lower melting points. Let us see structure of dichlorobenzene molecule. And in the first case student, the name of the molecule is 1,2-dichlorobenzene or ortho-dichlorobenzene. In this molecule student, the melting point is 256 Kelvin, whereas the boiling point is 453 Kelvin. Next molecule, that is meta-dichlorobenzene or 1,3-dichlorobenzene. In this molecule student, melting point is 249 Kelvin, whereas the boiling point is 446 Kelvin. And the third one, para-dichlorobenzene or 1,4-dichlorobenzene. In this molecule student, the melting point is much higher. It is 323 Kelvin and the boiling point is 448 Kelvin. Now students, let us consider about solubility. Alkyl halides are insoluble in water because they are not able to form hydrogen bonds with water molecule. However, they are soluble in organic solvents such as benzene, alcohol, ether and chloroform, etc. Whereas alkyl halides are insoluble in water but readily miscible with other organic solvents. Let us study about density. The density of haloalkanes increases with increase in number of carbon atoms present in the haloalkanes, or student, increase in the number of halogen atoms, or it can be increase in atomic masses of the halogens present in the given haloalkane. Now students, let us consider chemical properties of haloalkanes. Haloalkane students are highly reactive compounds, and their reactivity is due to the presence of polar carbon-hydrogen bond within their molecules. And the chemical reaction of haloalkanes can be divided into 4 different types. And the first one, student, which is nucleophilic substitution reaction, whereas the second one is the beta elimination reactions, third, reactions with metals, and the fourth, reduction reaction. So let us consider first reaction, that is nucleophilic substitution reaction. The bond between carbon atom and halogen atom in haloalkane, student, is polar in nature, and the reason behind this is halogen atom X is more electronegative in comparison with the carbon atom. So student, halogen atom would be drawing the shared pair of electron density towards itself, thus the bond is polar in nature. And students, due to the presence of partial positive charge on the carbon atom of haloalkanes, the nucleophiles can easily attack on electron deficient carbon atom of the given haloalkane, thereby resulting in the displacement of weaker nucleophile, that is the halide ion. Let us see one reaction, students. To understand the above statements, the molecule which is represented is haloalkane. In this, halogen atom gets delta minus, that is partial negative charge, whereas the carbon atom gets partial positive charge. And this is because of electronegativity difference between carbon and the halogen atom. Halogen is more electronegative compared to the carbon atom. Now student, if we add a nucleophile, then this nucleophile displaces or substitutes halogen from haloalkanes and attacks to electron deficient center, that is carbon atom, with the removal of halogen as halide anion, resulting in single covalent bond of nucleophile with the carbon. Thus student, we can conclude that the reaction in which stronger nucleophile displaces the weaker nucleophile are called as nucleophilic substitution reaction. In our example, student, this nucleophile is a stronger in nature, whereas the halogen is weaker nucleophile. Let us consider one example for this, students. With aqueous potassium hydroxide or aqueous sodium hydroxide, or with silver hydroxide, that is moist silver oxide is also called as silver hydroxide. So the above reaction occurs when an alkyl halide is heated with aqueous potassium hydroxide or aqueous sodium hydroxide or moist silver oxide, student, corresponding alcohol is formed. In this case, potassium hydroxide or sodium hydroxide or else moist silver oxide, student, they are providing the strong nucleophile OH minus, that is hydroxyl anion, and it displaces or else it substitutes halide from haloalkanes. Let us consider reaction for this. When alkyl halide, student, Rx, is treated with potassium hydroxide, that is aqueous, on heating, the removal of halogen from alkyl halide and potassium from potassium hydroxide. So potassium halide is removed with the formation of alkyl plus OH, that is ROH is nothing but alcohol. In this case, student, OH minus from the reagent potassium hydroxide has displaced halogen from alkyl halide. As a result, we get the product alcohol. Example, when ethyl bromide is treated with aqueous potassium hydroxide, then students, we get ethyl alcohol, along with that potassium bromide as the product. In this case also, student, OH minus is a strong nucleophile. It is displacing the weaker nucleophile Br minus. As a result, that Br minus would be combining with the K plus ion, that is potassium ion, resulting in formation of potassium bromide. And the main product is ethyl alcohol. Second, when alkyl halide is treated with sodium hydroxide, which is dissolved in water, that is aqueous, then student, the removal of sodium halide occurs with the formation of ROH, that is alcohol. Example, when methyl chloride CH3Cl is reacted with sodium hydroxide aqueous state, then student, removal of NaCl, Na from the reagent, that is sodium hydroxide Na, and Cl from methyl chloride. As a result, the compound which is formed is methyl alcohol CH3OH along with NaCl, sodium chloride. Next, student, when alkyl halide is treated with silver hydroxide or moist silver oxide, then student, on heating, we get ROH, that is alcohol, along with the alcohol, removal of AgX, that is silver halide. Because student, silver oxide plus water would be giving you silver hydroxide. You can either write moist silver oxide in the answer or else directly use the reagent silver hydroxide. Example, when ethyl bromide, students, is treated with aqueous silver hydroxide, then ethyl alcohol is produced with the removal of AgBr, that is silver bromide, silver from silver hydroxide, whereas Br from ethyl bromide. As a result, we are getting ethyl alcohol and silver bromide. Next, students, we shall study about reaction of haloalkanes with alcoholic potassium cyanide. When an alkyl halide is heated with alcoholic potassium cyanide, students, alkane nitrile or cyanoalkane is formed. Let us consider one reaction when alkyl halide, that is RX, is reacted with alcoholic potassium cyanide, then student, removal of potassium from potassium cyanide and halogen from alkyl halide occurs, resulting in alkyl cyanide or alkane nitrile along with potassium halide. Let us consider example when methyl iodide is reacted with potassium cyanide prepared in alcohol. On heating, potassium iodide is removed, whereas the formation of methyl cyanide along with potassium iodide. Methyl cyanide is also called as ethane nitrile. Now students, reaction of haloalkanes with alcoholic silver cyanide. When an alkyl halide is heated with alcoholic silver cyanide, alkyl isocyanide is produced. And this reaction, student, within amines, already you have studied about carbylamine reaction. Alkyl isocyanide would be produced. Let us consider general reaction when RX, that is alkyl halide, is reacted with alcoholic silver cyanide. On heating, students, you get alkyl isocyanide, that is RNC, along with the removal of silver halide, that is silver from silver cyanide and halogen from alkyl halide. So both these silver and halogen combine to form silver halide, student, whereas the rest of the part, that is alkyl group and cyanide group, both would be combining to form alkyl isocyanide. Let us consider example when ethyl bromide is reacted with silver cyanide, alcoholic condition. On heating, student, we get ethyl isocyanide with the removal of silver bromide. Next, reaction of haloalkanes with silver salts of carboxylic acids. When an alkyl halide is heated with silver salt of carboxylic acid, student, an ester is formed. Esters, you might be knowing, it has fruity smell. Let us consider general reaction when silver salt of carboxylic acid is reacted with alkyl halide. Then, student, removal of silver halide occurs, that is silver from silver salt of carboxylic acid and halogen from alkyl halide, thus forming RCOOR, that is ester is produced along with the byproduct as silver halide. Let us see an example when silver acetate, that is CH3COOAg, silver acetate molecule is reacted with iodomethane molecule or methyl iodide. Then, student, removal of silver iodide occurs, resulting in the ester as CH3, COO and CH3. So, student, you are getting methyl acetate as the product. Along with that, we are getting silver iodide. Next, students, we shall study about ambidentate nucleophiles. Definition: groups such as cyanides and nitriles possess two nucleophilic centers which are called as ambidentate nucleophiles. Cyanide group is a resonance hybrid. Let us consider structure of the cyanide. Carbon has the minus charge with one lone pair of the electron, and nitrogen even has one lone pair of electron. Then, student, one of the pi bond can be delocalized on the nitrogen, resulting minus charge on the nitrogen atom. The cyanide group is a resonance hybrid. Now let us understand mechanism of nucleophilic substitution reactions. Nucleophilic substitution reactions in alkyl halides can take place through either of the two different mechanisms. And the first one, student, is SN1 mechanism, whereas the second one is SN2 mechanism. Let us first understand about substitution nucleophilic second order reaction, that is SN2 reaction. In this case, student, when methyl chloride is heated with aqueous potash, methyl alcohol is produced. Consider the reaction: methyl chloride plus potassium hydroxide dissolved in water, that is aqueous, formation of methyl alcohol with the removal of KCl, potassium chloride. In this reaction, student, the rate of the reaction can be given as rate constant multiplied by molar concentration of methyl chloride raised to 1 into molar concentration of hydroxyl anion raised to 1. Therefore, order of the reaction would be 1 plus 1, which is equal to 2. It is a nucleophilic second order reaction. Let us consider mechanism for the SN2 reaction. When methyl chloride is reacted with aqueous sodium hydroxide, sodium hydroxide, students, forms a nucleophile OH minus, that is hydroxyl anion, and this would be attacking the electron deficient carbon atom of methyl chloride behind the plane, from behind the plane, resulting in formation of an intermediate structure with oxygen of hydroxyl group forming covalent bonding with the carbon atom. Thus, student, we get a transition state. From this transition state, cleavage of carbon Cl bond results, thus giving Cl minus as a nucleofuge or living group. In this case, inversion of methyl group occurs. As a result, SN2 reaction results in inversion of the molecule. The nucleophile OH minus attacks the carbon atom from the side opposite to that of the chlorine atom to form a new carbon OH bond, which can be observed in the transition state. So this results in complete inversion of the configuration. This inversion of the configuration is commonly known as Walden inversion. Many a times in exam they would be asking you about Walden inversion. So Walden inversion, students, occurs when SN2 reaction results in inversion of the configuration. Thus, we can conclude that the order of reactivity of alkyl halides towards SN2 reaction is: methyl halide is more reactive, student, compared to that of primary halides, and primary halides are more reactive compared to secondary halides, whereas tertiary halides are least reactive. Let us now study about substitution nucleophilic first order reaction, that is SN1 reaction. In SN1 reaction, students, which are carried out in polar protic solvents, that is water, acetic acid, etc. You need to understand about polar protic solvent. So water is acting as a solvent, and even, student, it can ionize to form H plus ion, and this is true with acetic acid also. Acetic acid, students, it can ionize to form H plus and acetate anion. So the proton, that is H plus ion, both in the water and acetic acid can be formed. So both are selected as a polar protic solvent for SN1 reaction. Now, hydrolysis of a tertiary butyl bromide with hydroxide ion gives us tertiary butyl alcohol with the removal of bromide anion. So let us consider reaction. The molecule student tertiary butyl bromide is made to react with OH minus. As a result, we get tertiary butyl alcohol. Actually, the reaction proceeds in a two-step process. Let us first consider about rate of the reaction and understand why it has to be called as first order reaction. Rate of the reaction, students, is equal to rate constant multiplied by molar concentration of tertiary butyl bromide. This results in the order of the reaction equal to 1. In this case, we are not considering the OH minus concentration. The reaction is of first order kinetics. Now let us consider mechanism for SN1 reaction, which consists of two main steps. The first step, formation of carbocation. So what is the meaning of the carbocation? The carbon having positive charge. So within first step, student, we are getting a product which is having carbon with a positive charge. Let us consider reaction with the same molecule of tertiary butyl bromide in presence of hydroxyl anion, students. It forms tertiary butyl cation and bromide anion. Nucleophile OH minus cannot attack the bromide anion from front side due to repulsion. Due to the repulsion between both the negatively charged nucleophiles OH minus and Br minus. Thus, student, OH minus would be attacking from behind the molecule. Now, in this case also what happens is nucleophile OH minus cannot attack bromide anion from backside due to steric hindrance, and the steric hindrance is caused by the bulkier group methyl groups. In case of tertiary butyl bromide, student, we are having 3 methyl bulkier groups which won't allow the backside attack of hydroxyl anion. Thus, student, the only possibility which has been already explained to you, that the tertiary butyl bromide has to form the cation and anion, that is tertiary butyl cation with the carbon having positive charge and bromide anion. So this would be formed only by the breaking of carbon-bromine single bond. And this step, student, that is step number 1 for the formation of tertiary butyl cation, it is the slowest step. And the slowest step is also called as rate determining step. In short, RDS, rate determining step of SN1 reaction. Now, student, question arises about the carbocation is planar and what is the reason? And the answer for this is because the central positively charged carbon atom is sp2 hybridized. Thus, the carbocation has got planar structure. Moving to the second step, attack of nucleophile on carbocation. In this case, student, tertiary butyl carbocation, which was formed in step number 1, is attacked by hydroxyl anion, and this process, student, is relatively fast, resulting in formation of tertiary butyl alcohol. Thus, student, we can conclude that greater is the stability of carbocation faster is the rate of the reaction. Step number 1 is a reversible reaction, and it is also rate determining step, and the reason for this, student, is bond breaking is much slower than bond making process. Thank you, students. In the next video, we shall study about order of reactivity towards SN1 reaction, stereochemical aspect of nucleophilic substitution reactions. Thank you.